that may be part of the reason. Sadly, that's actually part of the reason your homework's not written yet. So, anyway, all right. I'll try to stop dumping on the bookstore. The bookstore's great. The bookstore's wonderful. Nothing negative was said about the bookstore before this taping began. Let us begin with a word of prayer in a moment. All right. Dear Heavenly Father, we thank you for this day. I thank you for these students. Again, I just ask you to just bless this class, help us to glorify you, what we do, and just pray that your hand would be on this semester, Lord. In your name I pray, Lord Jesus. Amen. All right, so complex analysis is what? What is complex analysis about? Well, in a nutshell, what complex analysis is about is calculus, where you've replaced the real number system with the complex number system. That's basically it. And then it turns out that there are very interesting theorems that are interesting in their own right, but they also give you new insight into calculus that you've already studied. So that's one of the things I really like about this course is, yes, we'll learn interesting new theorems, but also if we take some time to be retrospective, we'll understand calculus that we already studied better. So I'm just going to start with the definition of the complex number system. So here's the definition for us, the complex number system. I'll just get straight to it. It's going to be equal to R2 as a point set, all right? So basically, it's x comma y such that, x and y are real numbers, right? But we almost never use that notation, all right? We're going to use the notation that x comma y is actually equal to x plus iy, right? So essentially this notation makes the unit vector in the x direction number 1, and it makes the unit vector in the y direction the imaginary number I. But anyway, that's it. This is a complex number. Now, typically, we'll write z equals to that, all right? So, admittedly, I'm already violating calculus 3 notation, right? Because in calculus 3, if you write a vector without a vector symbol, I will be unhappy. Here, if you write a vector symbol on z, I will strangle you. So no, but it is admittedly a 2-dimensional vector, all right? So then what? We can picture it, right? So for example, just be concrete here. This one right here would be something like z equals to, 2 plus 3i, right? That means we go 2 over, we go 3 up, right? As usual, this is the x-axis, this is the y-axis, but we also call this the real axis, and we call this the imaginary axis, right? Okay. Now, what would you like to talk about if you're talking about a point in the plane? Well, first things first, I would talk about the distance from the origin, right? What's this distance here? So you can tell me it's the what? The square root of 4 plus 9, right? So square root of 13 for my example, right? So here's the definition. I guess I'll write here. Definition, the length of z, or the modulus of z, is equal to the square root of x squared plus y squared. So this defines the length, or often we'll call it modulus, of z equals to x plus iy. Now, there is some danger for ambiguity here in terms of how do I know, let's just make a convention that when we write z equals x plus iy, we're understanding that x and y are real numbers, okay? We would write complex equations using complex variables, and they might look like that, but I need to let me stop. Not helping. So that's the length. So there it is. All right. Now, up to this point, I haven't really explained at all why this is the complex number system, right? I mean, what is this? What am I saying? To make this the complex number system, we have to explain, how to multiply complex numbers, right? Adding complex numbers, we already know that. That's just addition of vectors. Scalar multiplying by a real number, complex numbers, that's fine. That's just scalar multiplication. That's just two-dimensional vectors. We already know that, right? Calc 3. But multiplication, that's something new. So here's the definition. So here it goes. If I have z equals to x plus iy, and I'll make w equals to a plus ib, then zw, which of course is x plus iy times a plus ib, right? What's it equal to? There you go. Now you can see. So basically, we just proceed normally, right? This is a definition, so I don't really have to derive anything here, but the definition of how to multiply these is xa minus yb plus I times xb rather, my bad, xb plus ya. All right. So this right here is the very definition of complex multiplication. All right? What are the properties of complex multiplication? So how about like z times w is equal to w times z? You could prove that. All right? What else could we prove? We could prove that if we had z1 plus z2 times w, we'd get z1w plus z2w, right? What else could we prove? How about if we had, eta times z times w? Would that be equal to eta times z times w? You're like, what do you mean by that? Well, let me make that a little bit more textured. What I'm really asking is this true? Now that's actually something to talk about, right? Is multiplication associative? It is. In fact, it is associative, right? So multiplication is commutative, it's associative, you've got this distributive property. Anything else? So as you think about real numbers, right? Some of you have taken real analysis, I think, so you've thought a lot about real numbers. Some of you haven't, and that's also fine. But you've taken calculus, right? You think about real numbers. What do we do with real numbers? We add them, we subtract them, we multiply them. What's the other thing we do? Divide them, right? So we should talk about that. And what else? If I give you 5, and I give you 5, I give him 10, who's got the bigger number?
Ordering.
Right, yeah. There's ordering for the real numbers. So how about complex numbers? If I talk about 2 plus 3i, right? What if I talk about minus 2 plus 3i, right? Over here. Which one's bigger? Which one's smaller? They do have the same magnitude, but so yes, you can order complex numbers in that sense in terms of like how far they are from the origin, but you're really back to a real number then. You're not ordering them, right? The fact of the matter is there is no ordering of the complex numbers that also respects the algebraic structure of it. You can like order pretty much any set, but the ordering that you would give to the complex numbers as a set is not an ordering which plays nice with the algebraic structure here. In contrast, the real numbers are a complete ordered field, which makes them special. All right, anyway, so properties of complex multiplication, here they are. We'll get back to the division, that's a good question. There's something else we can do with complex numbers, right? Definition, complex conjugation. All right, so if I have z equals to x plus iy, then z conjugate, z bar, is equal to x minus iy. Yep.
If the reals are a complete ordered field, what are the complexes?
Well, they're a complete field. I should make that a homework problem. Yes, I will do that for you. So it was already in my plans. But the complex numbers are special for reasons that we'll get into.
Algebraic closure?
Algebraic closure, mainly. Yep. So let's see here. So complex conjugation is this, right? Geometrically, how's that going? What does that look like geometrically? If I have up here z equals x plus iy, where's the conjugate?
Flipped over the x-axis?
Right, yeah, it's over here. It says like reflecting over the x-axis, yeah, just like you said. Right? So what would it mean, for example, if z was equal to z bar? Right? Then, yeah, y equals to 0. We say z is real, right? Z is real if z is equal to z bar. What would it mean if z was equal to minus z bar? Or if you like, I'll write it this way. What if z bar is equal to minus z? I'll write it that way. Then what? Then x is equal to 0, right? And z is equal to iy. It's called pure imaginary, or sometimes you might just call imaginary. But I kind of like pure imaginary for more. Right? Now, if you read my notes, and I hope you do, there's a lot I say in the notes that I don't say in class because, well, class is short and my notes are, yeah. And I have a lot of quotes from like Gauss and others, and I think it's really interesting to see how much Gauss hated the terminology imaginary, basically, right? Because this terminology imaginary, or they used to be sometimes called like fictitious, which is probably just like another translation of whatever Gauss actually said in German into English, right? But I mean, I don't know what actually Gauss said. But basically, that terminology has made people scared of these things more or less since its introduction, right? But in some real sense, pun intended, complex numbers are every bit as real numbers. All right, they have an objective existence in as much as math does. I mean, you can construct them. All right. In fact, in the notes, I give 3 different constructions. The one is like what I'm using as our primary definition here, the plane, right, where you can define this using an abstract multiplication with like a star, and you can prove from that abstract definition all these properties follow. All right, that's one way you can do it. Another way you could build complex numbers is from 2x2 matrices of the form like A minus B, B, A. Those 2x2 matrices, if you multiply them, matrix multiplication has exactly the same structure as the complex numbers. Those are, if you've had abstract algebra, they're isomorphic to the complex numbers. If you had more abstract algebra, another way you can build the complex numbers is from taking polynomials with real coefficients and dividing by the ideal generated by x squared plus 1. If you do this, the ideal represented by x behaves as the number I. That is not our definition in here because that would be very unkind to the engineers who haven't had 2 semesters of abstract algebra, right? But at the end of things, that's actually a very nice way to think about things. Now, we don't need all that. All we need is the complex number system. And essentially, the complex number system is defined by its properties, which I have on the board here. All right? Okay, so we got this complex conjugation. Some numbers are real. Some numbers are imaginary. What does it take for a complex number to be quote-unquote complex? What's that usually mean in the common vernacular? That would mean what? Real or imaginary, but usually when people say a complex, they're at least assuming the possibility that the imaginary part could be non-zero, right? That would be the distinction between a complex variable and a real variable, perhaps. Okay, can you guys tell me anything about complex conjugation? Does it have any interesting properties? How about this? What if we were to calculate z plus w conjugate. How would that go? So I'm going to use 1-2 notation for a change of pace here. So suppose I've got like x1 plus ix2 plus, oh man. All right, let me try again. z1 plus z2. I'll get it eventually here, guys. I have trouble making choices. x1 plus iy1 plus x2 plus iy2. There you go. Conjugate all that. How do you do that? Well, we have to understand that that's what? x1 plus x2 plus I times y1 plus y2. What did I just do, actually? I just used the definition of addition for complex numbers, which I haven't even written, but we're assuming is understood, all right? If you really drill back into what I'm saying, I'm using the definition of addition of vectors in the plane as it's seen in this notation. That's what's going on. Anyway, I don't think that's a terribly interesting step. I don't require you to justify that kind of step. You just do it, okay? All right? Otherwise, this will devolve into like a proofs class more so than I want it to be. I want to keep the proofs emphasis on things that are actually a little bit difficult. So x1 plus x2 minus what? I times y1 plus y2, right? But then if we put things back in order, what do we got? We've got z1 conjugate plus z2 conjugate, right? In other words, what this calculation shows is that the conjugate of a sum is the sum of the conjugates, all right? Now, something I usually assign as a homework is for you guys to prove that z1 times z2 conjugate is equal to z1 conjugate times z2 conjugate. Exercise. All right? Work, yes, sir.
You had said that C was isomorphic to a group of matrices. What would the conjugate be represented as in those matrices?
Transposition. Yeah. It's like x maps to minus x in the polynomial ring. But anyway, that's a weird question. I like it. So questions which make me like chase a rabbit like far away from what I'm actually supposed to be lecturing on. They're usually good questions, but I need to develop more discipline to ignore them. So I should repeat the comment I should say after. I should be like, that's interesting. Come talk to me about that in office hours. These are words I should say. Anyway, but I never say that pretty much. But anyway, so this is not as trivial as that. This will actually require you to multiply the complex number out. And then this, you have to multiply. It's not hard. It's like 3 lines, but you can do it, all right? I'll let you do it. Let's see something else, though. What happens if we look at z times z bar? We got what? X plus iy, x minus iy, right? How's that go? What happens there? I heard something about modulus. So you say x squared plus y squared, right? And yeah, so
which is the square of the modulus of z.
Ah, yeah. So that is exactly what you said. It's the square of the modulus. So, hey, theorem, right? Theorem, modulus of z is equal to the square root of z bar. That is definitely something worth remembering and using. All right? Now here I'm talking about the positive square root that you have known and loved since like 5th grade. We will soon talk about square root in a more interesting way. So stay tuned. Now, that's kind of neat, right? It's reminiscent of the dot product formula from Calc 3, right? A little bit. So how about this? What if I calculate the length of a product of 2 complex numbers? How's that go? what would that be? Well, it would be the square root of ZW, right, times ZW bar, using my newfound theorem. And what's that? Well, by properties of complex multiplication, that's ZW, Z bar W bar by your by the homework that you're going to do, right? And then complex number multiplication commutes. So what you got? You got square root of ZZ bar times the square root of WW bar. I skipped a step there because I'm starting to get. Anyway, so of course the square root of a product is the product of the square roots, right? And I'm still not in any danger because these are separately real numbers, right? So I'm within my bounds to use regular square root there. What is that though? Length of Z, length of W. Let's put this into words. What's this saying? It's saying that complex multiplication, whatever it is such that when you multiply complex numbers, the length of the product is equal to the product of the lengths. That's actually pretty interesting, right? That's still true for real numbers. It's just not especially interesting, right? Like, what's the length of a real number? Absolute value, right? Length of minus 5 is absolute value of 5, which is 5. So if I say, like, what's the length of minus 5 times minus 7? Well, it's 5 times 7. It's 35. So that's just the fact that the absolute value of a product is the product of the absolute values. That's still true for the modulus here. Now, some people will call complex modulus absolute value, and that's fine, right? There's a reason for that, because it is very much like an absolute value, right? All right. In fact, what else could you tell me? Things we could prove. If we had the modulus of Z plus W, excuse me, oh goodness gracious, that would be what? Less than or equal to modulus of Z plus the modulus of W. This is called the triangle. The triangle inequality. Very good. There's also, this, probably should put this first, but the modulus of Z is equal to 0 only if what? Z is 0, right? That's also true. And what else can you tell me about modulus? Well, the modulus of Z is, of course, greater than or equal to 0, right? And it's equal to 0 only when it's 0. These things are true. Yeah. So let's talk more about complex multiplication, because this gives you part of the story, right? But if you're talking about a two-dimensional vector, how can you uniquely describe a two-dimensional vector? What is there? There's a magnitude, and there's also an angle, right? Or better yet, a direction. So if I find a good, I guess I'll keep over here, sorry. So if you think about it, right? If I talk about Z up here equal to x plus iy, right? If this is the standard angle theta, right? Can you tell me what the legs of the triangle are in terms of your, trigonometry? What we got here?
The bottom one would be x and the top one would be y.
Yeah, that would be x, right? And this would be y. Now, I'm drawing it in quadrant 1, but you understand that in quadrant 2, we'd have x negative, y positive. In quadrant 3, we have both negative. In quadrant 4, we have x positive, y negative, right? All that jazz. And also, the formulas I'm about to write down are equally valid in all 4 quadrants. In fact, that's essentially why we make polar coordinates as such. So I'm about to write r cosine theta, which I think is a consequence of not enough sleep. But there we go. That's better. Okay, great. What does that mean about z? Z is equal to x plus iy, right? But that's apparently r cosine theta plus I times r sine theta. And what is r? Exactly, that's our usual notation. We use modulus of z there. But if you like, for a specific application, we can give it another name, like r for a calculation, that's sometimes useful because writing r 10 times is much easier than writing slash z slash 10 times, especially when you're taking it to like a anyway, just, you know, think about it. Make the notation work for you, don't work for the notation. Cosine theta plus I sine theta, we can factor out here, right? In complex variables books used to use cis theta here. I objected to that 10 years ago. I object to it even more now. So I refuse to use this notation. I do not like cis notation. And this, on the other hand, we should call it what it is. This is e to the I theta. That's the right notation for this. In fact, what I'm doing right there is I'm making a definition. E to the I theta is cosine theta plus I sine theta. This is sometimes referred to as Euler's formula. It can be derived from a larger discussion about power series, which we'll get to eventually. But for now, let's make it a definition. Accepting this as the definition, which I'll write over here, what can we say about it? Yowzers. My eraser shirt is letting me down. I must have watched the eraser shirt. So sad. All right, so definition. E to the I theta is equal to cosine theta plus I sine theta for any theta, which is, let's say, a real number, okay? I think Euler wrote this down around 1749, right? So it's somewhat mysterious to me how people say that like Gauss and others invented the complex plane in the 19th century. Like, I don't know, if you write this formula down, it seems to me like you have the geometry of the complex plane well in hand, right? Like this has so much of the geometry of the complex plane right in this formula. See, because you can prove, exercise, that e to the I theta times e to the I beta is equal to, guess what? E to the I theta plus beta. Now, that's not obvious. The reason that's true, if you multiply e to the I theta times e to the I beta, you get like cosine cosine minus sine sine, you get sine cosine plus cosine sine with opposite theta beta. So by the adding angles formulas, bam, you got it, yeah.
Could you also use exponential identity?
No,
Why not?
because we defined the exponential like that. So this is not the exponential you're looking for. Now, if you had also, I should say what I was saying earlier, but
I mean, wouldn't you want to just analytically continue the Taylor series?
we don't know. Those things you're saying are like hieroglyphics to me. I don't know what you mean. So, yes, if we had defined the exponential with a power series approach, we could derive it, sure. And you can prove the law of exponents from the Cauchy product of power series, sure. Which is, you know, yes, we can do those things. But here, I'm making this is the definition, and you can prove it just from laws, adding angles, formulas for sine and cosine, just like that. And once you have that, you know, if you have z is equal to e to the, so we have z is equal to the modulus of z times e to the I theta. We have w is equal to the modulus of w times e to the I beta. What happens when we multiply these two guys together? We get, you know, modulus of z, modulus of w, right? E to the I theta, e to the I beta. But by what I was just talking about, that's the length of zw times e to the I theta plus beta. So, I mean, two things. When we multiply complex numbers, the length of the product is the product of the lengths. And where it is the sum of the standard angles. So definition. If z is equal to modulus of z times e to the I theta, where, you know, z is not equal to 0, then theta is an element of arg z. This is the so-called argument of z. All right. This class goes to 4, right?
3:30.
Oh, 3:30, okay. See? Class just got shorter by a whole half hour. I feel better, right? You feel better? I feel better, no. So the argument of z is what? Is that, I mean, what is, yeah?
A set.
It's a set, right? And how do you know that? Like I read the book. No, maybe, I don't know. Now, yeah, it would be a set, you see, because, let's see here, how can I say it another way? Let's suppose we had, for the sake of discussion, z is equal to, you know, like modulus of z e to the I theta 1, and that's equal to modulus of z times e to the I theta 2, right? Suppose you have two different angles. How are they related? So first of all, when we have, think about this, if you have two complex quantities equal, there's two different obvious things you could do. The one thing you could do is you can equate the real part to the real part and the imaginary part to the imaginary part on both sides, right? That's one thing we can do. Another thing we can do is we can say, well, the magnitudes have to match. You could say that the directions have to match in terms of unit vectors, right? But you can't say that they have the same standard angle unless you make a choice, right? Yeah?
Cosine and sine are both periodic.
Right, so exactly. So what this means is that e to the I theta 1 is equal to e to the I theta 2, right? And that, by our definition, right? No power series, sorry. All in good time. We'll do power series out the wazoo. Just give me a minute. For some of us, the sting of power series from Calculus 2 is still fresh. I'm trying to build a little bit more daylight between that, and that's one of the kind of scary things about this book. Is it like it's like power series and like page 5. I don't know. Oh. That's a good answer. I like that. So here we go. And then someone just told me cosine and sine are 2 pi periodic, right? But I would point out to you that this equality is a complex equality. It gives us two things. Right? This is really, just to beckon back for a second here, what we're really doing, right? We just don't want to write this, right? If we wrote everything in this notation, man, it would just be a drudgery, right? But that is what it is. It's the equation of two-dimensional vectors. So the first part has to match, the second part has to match, which gives us two separate equations, namely that cosine theta 1 equals to cosine theta 2, and sine theta 1 equal to sine theta 2, right? And that says what? That says that the difference of the thetas, like theta 2 minus theta 1, has to be an element of 2 pi z. In other words, theta 1 minus theta 2 is equal to 2 pi times an integer, right? So, all right, so it's useful then to make a choice. And so here's the definition. Arg z. You're like, I thought you already said arg. No, I'm saying arg. Arg z. All right, sorry. It's horrible. No, I regret nothing. Is an element of arg z intersected with minus pi not included to pi included. So this is the so-called principal argument of z. This is our standard choice of standard angle in complex analysis. It does not suffice for our purposes in our application. We need notation to clearly choose angles of a specific range. All right, so I'm going to introduce some additional notation past this, but that's just to start with. There's your principal choice. And so with this choice in mind, little arg of z would just be equal to big arg of z plus 2 pi times the integers. You could write that. Yep.
Is it just by convention that negative pi to pi is chosen and not like 0 to 2 pi?
It's convention, right? Yeah. Now, I have found it useful to introduce some more notation here, so let me share that with you guys, if I can find it. Where'd you go? Where'd you gone to? This is on page 7 of my notes. So, so you say you want to use 0 to 2 pi, huh? I got a notation for that. Now, one of these notations is from, I believe, from Churchill, which, like, Dr. Sperano and I both had complex out of Churchill. So that gives you some sense of how old that is. But anyway, so here's my other notations. Arg alpha plus of z would be equal to little arg of z intersect with alpha minus 2 pi, comma, alpha included. And then arg little alpha of z would be equal to arg of z intersected with alpha included to alpha plus 2 pi not included. So the choice of angle that you're looking for, you might call argo. Like, I could say this: 0 is less than or equal to arg sub 0 of z is less than 2 pi, for example. Yep.
Do you need to know those other two? Or is that
Yes. Yes, we need to know these. So let's actually look at an example. Let me find all 4 of these monstrosities. I mean, I can't tell you what it is for alpha arbitrary. Like, I need to make a choice of alpha, otherwise, yeah?
So are those two both sets containing one element? Or
Yes, and I mean to say the element, not, I mean, fine, I mean, you got me. Maybe I should say element of. Fine, I am fussing about this. You're not wrong. I will edit my notes accordingly and make them more unreadable for the engineers. So, you're welcome. It's a set containing just one element. So I don't want to say that the element is equal to the set containing one element. Nothing good comes from that. But ignoring that also is the path to a significant decluttering of many equations. So I don't know. It's I don't know. What can I tell you? It's yeah. Okay, so you've been moving the camera, yes? Okay, thank you. Let's see here. Let's example. What are we on? Example 2. Okay, so suppose you have z is equal to, I'll do something that's relatively easy, 1 plus I. All right. What's the length of 1 plus I? Square root of 2, right? What's the angle of 1 plus I? 45 degrees, which is dead to us. That's e to the I pi over 4. All radians all the time in here. All right, because we do calculus. You don't want to do calculus on degree, sine, cosine, but yes, 45 degrees is actually how I think, admittedly. I'm even more schizophrenic on that issue in Calc 3. Like, yeah. But yes, now this is what's called the polar form of the complex number, all right? Magnitude times e to the I theta, this is polar form. Polar form is not unique, right? Because of the 2 pi integer degeneracy of the standard angle, right? But this is a polar form, all right? In fact, it's the principle. I mean, this is, well, I can tell you, what's arg z then here? Well, it's pi over 4, right? Why? Because that's where. So this down here would also tell me minus pi is less than arg z. Oh, I had element of over here, didn't I? I'm nothing if not inconsistent there. Oh well, don't worry. I'll take points off your homework so you know what matters. Sorry. And so pi over 4. What would, this would also be equal to your choice of angle, right? In this case. What if I did like arg, oh, I don't know, 3 pi of z? What would that be equal to? Where would arg of 3, where does this have to be? It's between what? 3 pi less than the angle we're looking for, right? Less than what's, that's what? Less than or equal to 3, less than or equal to 3 pi, right? By my definition. Less than what? 3 plus 2, 5, right?
So 13 pi over 4?
Oh, you're probably right. Ah, my brain. Yes, thank you. Are we good? This actually matters. It's like the fundamental difficulty of complex analysis, really, in some sense, calculationally, is choosing an angle. It doesn't seem like much here, but it will become the issue in other problems. So I wanted to have some really clean, useful notation for us to make non-standard choices of angles. That's why I'm introducing these here. I will use them again as we go on, okay? Oh, one other thing. What's arg? Little arg. Little arg z here is a set, right? So I'll write it as a set this time. Honest to goodness set. It is pi over 4 plus 2 pi, let's say j, such that j is a integer. And I've just been kind of glibly writing this as what? Pi over 4 plus 2 pi z. But that's what I mean by that kind of equation, right? How do we add a number plus a set? It's understood to be the sum of every element in the set plus that number. That's our definition of addition of set with number, right? We can also add sets, right? How would you add two sets? Union. No. That's not what I mean by it. If I do like arg of z1 plus arg of z2, I don't mean union of those. I literally mean theta 1 plus theta 2 such that like theta 1 is an element of arg z1 and theta 2 is an element of arg z2. That would be what would be meant there. I don't know if that's union or not. It might be. I just don't. Yeah, I don't. So, but I can tell you this, and this is actually a pretty good homework problem. That's true. However, this is not true if you capitalize those arguments. If you insist on your angle coming from a specific choice of 2 pi radians, one side not included, when you add those together, you don't have to be within that 2 pi period. You can escape. It may or may not be true. So there are. So this is the frustration of complex analysis in some sense, is that you deal with these sets of values, which properly speaking are what? These are not single valued, right? What was the first question on the first test in Dr. Sprano's Calculus 1, if any of you had it? It's been a while since he's taught it. I'm talking to no one. But he used to always ask the question, what's the definition of a function? That's like his first question on the first test in Calc 1. Like, that's important. It's single valued, right? These are not functions. All right? And that's these in the ubiquity of these expressions and the analysis of these expressions in 19th century mathematics is part of why mathematicians had such a hard time finding a clear grasp of the function concept, is because they were so immersed in solving equations. And to solve equations, it's often more convenient to think about multiply valued things in this complex context where you have an infinity of solutions for certain problems, not just a unique solution. We'll see this issue as we go on. All right. Oh, good. I still have 45 minutes. Let's see here. Was it this too soon? No? All right. What else can I tell you? So the one thing, of course, that what's your name again?
Ben.
Ben was trying to get me to talk about division. That's a good idea. Ben wants to divide the class. So, actually, it doesn't sound so good, actually. If, so here it is. If z is not equal to 0, right, then z bar is equal to what? Well, it's equal to the modulus of z squared, right? Which is a real number, right? So what's this tell you? This tells you that z times z bar over the modulus of z squared, right, is equal to 1. So what would we mean by z inverse, the multiplicative inverse of z? It should be whatever we multiply by z and get back 1. What does this say? So therefore, theorem, z inverse is equal to z conjugate divided by the length of z squared. There you go. That's a formula for the multiplicative inverse of a complex number. Simple as that. We can make this more complicated. I can show you homeworks I've given in previous years. I have ways of making this way more complicated, but that's really it. When does this formula work? You're like, I want you to keep it more real. Keep it more real, sir. So example 3, maybe? What if I have, I don't know, z is equal to, how about 1 plus I? We like that one. All right. So what's 1 over z? According to my formula, we do 1 minus I divided by what?
Square root of 2.
But
Oh, square root of
2, yeah. Now, if you did this math in high school, this is probably not how you did it, right? How did you do it? Do you guys remember? Don't deny my dream. High school still teaches you complex arithmetic. It happens. Some of you are in like classical conversations or something. They do it there, right? Wait a minute, is this in Saxon? I don't know. Let's see, 1 over 1 plus I. Here's how I would typically approach it in a complex class. Goodness gracious, calculus is what I was trying to say. I multiply by 1, like so. Goodness, I should just stop now. I should just stop. So I multiply by the conjugate over the conjugate, right? This is called conjugation, right? And then what happens? You get 1 minus I, then downstairs you get 1 plus 1. The I and the minus I cancel, and lo and behold, 1 minus I over 2. Hooray! Yeah.
In our sort of initial definite theorem, didn't we sort of assume that division existed in order to sort of say that division existed? If that makes any sense?
Well, I can certainly write homeworks to try to explore this in more depth. But ultimately, I'm really just relying on the fact that multiplication is essentially, this is a real number, right? So I'm not assuming division of a complex number. I'm assuming that the division by a real number makes sense, which is to say that scalar multiplication makes sense for complex multiplication, and we could prove that. But if you're uneasy about me assuming the result here, I can show you. I mean, I have ways of deriving it more.
I figured.
So let's take a look at this a little bit more here. This thing we just did. What's that look like in the polar notation? What's going on here? What was the polar form of 1 plus I? We had, come on. So I had z is 1 plus I, but we could also write that as square root of 2. Right? So what's 1 over z? 1 over square root of 2, e to the I pi over 4, right? And actually, I'm assuming that this note, admittedly, you're just arguing by notation, fair enough, right? You got me. But we can prove a theorem which says that e to the I pi over 4 inverse is actually equal to what? Care to guess?
Negative I.
Yeah, e to the negative I pi over 4, right, yeah. And so that's how this goes.
That's just promising me you're doing Taylor series.
No, it's really just something else. But yeah, we'll get there. I think it's just, I mean, all right, fine. If we have, generally speaking, if we have z equal to, let's say, e to the I theta, right? Then that's not equal to 0, right? Point number 1. So we know its multiplicative inverse exists if you're willing to accept my slightly shady calculation, right? Then what? What's the inverse? The inverse is equal to, yep, so I'll write it out because we don't know yet. Cosine theta plus I sine theta, conjugate, divided by what's the length of e to the I theta? Well, cosine squared theta plus sine squared theta. I mean, not the length, but the length squared. Modulus squared goes in the denominator, right? But that is 1. And upstairs, you got cosine theta minus I sine theta over 1, also known as e to the minus I theta, using the fact that cosine is even and sine is odd to pull the minus in appropriately. So that proves this calculation. That's why I was able to go from here to here. That's yeah. Now, all right. So, okay, so we know what inverse is, all right? Example 4. I'll show you something. All right, suppose somebody comes to you and says z is equal to, oh, I don't know. I'll keep it simple enough here, minus 1 minus I. Find polar form and Cartesian form of, oh, I don't know, z to the 100. How should you do this? How should you not do it? You're like, well, I know the binomial theorem. So I can look up the binomial coefficients for the 100 power and just rattle. No, don't do that. Right? The way to do this is to convert it to polar, right? Which is what? Z is equal to the square root of 2 again. Sorry, I'm kind of being boring. E to the what? E to the I. Yeah, not pi over, well, it's not pi over 4 here. Notice that minus 1 minus I is like down here. We could either go with a minus 3 pi over 4 or with a plus 5 pi over 4. So I'm trying to keep it positive today, so I'll go with 5 pi over 4. Sorry, that was horrible. I regret nothing. And I will now use the theorem we have not proved, which that feels like a homework problem. De Moivre's theorem. So z to the 100, that's actually a pretty good homework problem. It's not hard. It's really just induction. So the theorem is this, guys. E to the I theta to the n power is equal to e to the I n theta for all n in the integers. This is so-called De Moivre's theorem. That's actually a really slick notation for a tower of incredibly interesting identities involving sine and cosine. The amount of data that is like folded into this notation, it's staggering what's in that equation. It's really deep. But anyway, we can use it to solve this problem. To raise the 100 power, guess what? We just do the square root of 2 times e to the I 5 pi over 4, all raised to the 100 power. All right? And then what? Well, you got the square root of 2 raised to the 100 power times e to the I, what's 100 times 5 pi over 4? Well, it's, I do believe that's 125 pi I, right? Right? And using the 2 pi periodicity, I can erase the 125 and just drop it back to pi I. What's e to the pi I? -1 is right, because cosine of pi is -1, sine of pi is 0. That's how he knew that, right? Or maybe he saw a t-shirt. I don't know.
High school.
High school. What's square root of 2 to the 100? It's also known as 2 to the what? 50? Is that right? So, oh, minus 2 to the 50. There you go. That is the Cartesian form of this. The Cartesian form of the answer, it's a real answer, and that's it. What's the polar form of the answer? It was, well, one polar form of the answer is right above. But you could also write this as 2 to the 50 times e to the pi I. I kind of like that for the polar answer. You know? Man, I wish I had 10 more minutes. We were right on the cusp of something really interesting. So the next thing we do is we solve the equation. We solve the equation like z to the n equals to w. We're going to solve this equation in the complex domain. And we're going to see that using, basically the solution goes like this. We take it, we write it in polar form, we equate the magnitudes, and then we make the arguments for the two sides match up according to the 2 pi periodicity. In doing so, we find that there are n distinct solutions. And once we have this, we can factor polynomials over the complex plane easily. Let me show you an example of the factoring for the end of today. See? I learned, you know where I learned that? That's right. So z to the 4th, you know, let's see, z to the 4th plus 1, right? Oh, that's too easy. Z to the 4th plus I. How would you factor that? Well, that's z to the 4th plus e to the pi I over 2, right? And so let's see, if I divide that by 4, it turns out that the so-called principal fourth root of I is actually equal to e to the pi I over 8. All right? And then, knowing that, this factors like this. Z minus e to the pi I over 8. Z minus I e to the pi I over 8. Z minus, well, rather plus e to the I pi over 8. I may be doing this, no, minus, right, and then z minus, plus I think it is.